In this video, we're going to take a look at section 3.5 on graphing rational functions. Whoops. Sorry about that. Had a little bit of a technical glitch there. Okay, so the first kind of problem that you will encounter in section 3.5 is to find the domain of these rational functions. And I kind of feel like maybe I'm missing a piece of information here because I haven't really even told you what a rational function is. So maybe let's go back to this screen, and since I don't have the definition typed out like I should, what is a rational function? Let's just go ahead and write that in right here. So a rational function is a function of the form p of x over q of x. So it looks like this. It's a fraction. So again, whenever we use the word rational in algebra, it means we're talking about a fraction of some kind. So a rational number is a number that's a fraction, like 3 over 5. A rational function is a function that's a fraction where the numerator and the denominator have to be polynomials. So p of x is a polynomial and q of x is a polynomial. So that's the restriction here for it to be considered a rational function, is that we have to be dealing with polynomials on the top and bottom of this fraction. This will preclude fractions that would have like square root of x, negative exponents like x to the negative second power in the numerator somewhere. So maybe some of the worst kinds of fractions that we could have had will be filtered out by requiring that the numerator and the denominator are polynomials. That being said, these are still pretty sophisticated functions, and there's a lot to explore here. So one thing we're going to look for is the domain. And we've talked about this multiple times in the course. You never want to divide by 0, and so whenever there is a fraction involved, that should be your first concern, is let's be sure not to plug in any numbers for x that would make the denominator equal 0, because then I'm dividing by 0, and that just breaks the equation. It produces a null result, right? We get a, it doesn't compute, right? I'm trying to think of strong enough language to indicate the issue there. You can't divide by 0. It doesn't give you a value. It doesn't work. If it doesn't work in the equation, it doesn't work in the graph either, right? So this is going to be important for graphing, which we're about to do in a few minutes. So to find the domain of a rational function, you just set the denominator equal to 0 and solve for x. And the solutions that you find are the numbers that x is not allowed to equal. So by going through that process, you're finding out what x is not allowed to equal. The domain, of course, is the opposite of that. The domain is what x is allowed to equal. So the domain is everything but those numbers that you're finding when you set the denominator equal to 0 and solve for x. All right. So again, I like to start with the assumption that my domain is all real numbers. Then I find these values of x that would make me divide by 0. I pluck those out, and whatever I'm left with would be my domain at that point. All right, so let's give this kind of problem a try. So find the domain of the rational expression. They really should call it a function here. So the directions are I think it's a little bit of a misnomer. All right, f of x equals 3x squared minus 1 over x to the third power minus 36x. We only want to find the domain here. So we're going to be doing more stuff with these kind of functions in just a second. And so once we kind of get into that, just make sure when you see this problem on the test and when you see this problem on your homework that you don't go overboard and do all this extra stuff that you're not being asked to do here. It's a very simple thing. Well, maybe not very simple. Simple relative to the other stuff that we're going to be looking at. What we're being asked to do here is just find the domain. That's it. We're not being asked to graph it. We're not being asked to find anything else. Just what is the domain of this function, right? And that will be determined by the denominator, right? So the numerator actually doesn't even matter for this exercise. My concern is what numbers would make me divide by 0, because I want to exclude those from my domain. And so I'm going to start with all real numbers, exclude the numbers that would make me divide by 0, and whatever I'm left with, that will be my domain. So I'm just focusing in on the denominator. When would this denominator equal 0? So the process is to take the denominator and set it equal to 0 to find out, right? You could maybe guess what numbers would make this equal 0. You might even find one or two numbers that would do that. But remember, we learned earlier in this chapter that if you take this denominator and set it equal to 0, that's a polynomial equation. And we know the degree of that polynomial is the number of zeros or roots that we should find to that equation. So in fact, there are 3 numbers here that would make this denominator equal 0. And like I said, you might find one of them. I think one of them can be obvious if you think about it. You know, that one, there's one that kind of stands out to me anyways. But the other 2 are going to be a little bit harder to find. And you might actually stumble across one of those even. But then I would be surprised if a student could look at this and tell me all 3 of the numbers that would make that equal 0. So you need to set up this situation as an equation and then solve it. And let the equation tell you what would make it equal 0. So you don't want to waste your time trying to guess. That's what we did before, right? So back in chapter 1, we had these rational equations, right? And we'd have things like this. Now this one you can just look at and tell. -2 is the number you don't want to use here because that would make this equal 0. You can just look at it and figure it out. But that's not going to be possible, or not as easily done anyways, in section 3.5. So, and if this was difficult to do here, the process would be the same. If I want to know when this denominator would equal 0, I would set that denominator equal to 0 and then solve for x, and it would tell me. It would tell me x equals -2 is what would make this equal 0, which means I don't want that, right? I don't want x to equal -2 in this fraction because I don't want to divide by 0 because it leads nowhere. It's a dead end, right? So anyways, back on this problem here, same idea. I want to know what numbers would make this equal 0, but this time it's harder to tell just by looking at it. So instead, we'll just set up an equation by taking the denominator, setting it equal to 0, and then let the equation tell us the numbers that would make this equal 0 instead of us trying to guess or just try to figure it out by looking at it. Sometimes what I like to put here as a heading to remind myself what I'm finding here is these are the values that x is not allowed to equal. This is what's not allowed to happen, right? I don't want this to equal 0. This is what I'm trying to avoid, but I have to investigate it in order to find out what values of x I shouldn't plug in. So I'm setting it equal to 0 because that's what I don't want to happen. All right, anyways, I'm espousing a little too, you know, my exposition is a little too lengthy here on this particular problem. So let's just get to the answer here. So set it equal to 0 and then solve that equation. Now it's a polynomial equation, which we have seen throughout chapter 3. And the first the first preferred technique to solve this equation for any polynomial equation would be to try to factor it. If it can be factored, that's the best way to go about solving a polynomial equation. If it can't be factored, at least, you know, in an easy way, I guess, you know, when you think about it, all the techniques we now know involve factoring at some point. So you could really argue that they all involve factoring. But what I'm alluding to here is I don't want to use P's and Q's and do synthetic division if I don't have to. So if I can find another way to factor it without doing all the P's and Q's stuff in synthetic division, that's the way we want to go. But just keep that in mind, that if this could not be factored easily, that you could try to solve it by doing the P's and Q's, coming up with a list of possible zeros, checking numbers off of that list by using synthetic division until you find a number that gives you a remainder of 0, and then from there you could factor it, right? But this, thankfully, we don't have to go through all that work. And I don't know that there is a problem where you will have to do that, but I'm just saying worst case scenario would be to solve this equation, you'd have to do the P's and Q's and all that stuff. But I don't know if you'll come across one like that. All right, this one can be factored without all of that, right? There's a common factor of x, so we can factor out x. That's going to leave me with x squared minus 36 in the parentheses. And now that I have it down to x squared, that's quadratic. And that's something I know how to factor even further. It factors as x plus 6 times x minus 6. This x copies down. Now we set each factor equal to 0, and we get 3 numbers. We get x is equal to 0, and that's the one that I had in mind that you might be able to figure out just by looking. Right? If you plug in 0 for x, that would zero this whole thing out, and you'd be dividing by 0. But these two are a little bit more difficult to figure out, right? So we set this factor equal to 0, solve for x, we get x equals -6. We set this factor equal to 0, solve for x, and we get x is equal to positive 6. All right. And again, this is what's not allowed, right? X to the third power minus 36x is not allowed to equal 0. And so that means x is not allowed to equal 0. X is not allowed to equal negative 6. X is not allowed to equal positive 6, right? These are the numbers that x is not allowed to equal. So the domain is everything but these numbers, right? So the domain, if I had to write it out in words, would be all real numbers except 0, negative 6, and 6. Those are the three numbers that are off limits, but anything else can be plugged into that function. It probably doesn't work out nice most of the time. So some students, I think, look at that and go, well, I wouldn't want to plug in, any numbers to that thing, right? Because like most of the time it's going to be a horrible answer, but you do get an answer. That's the point I always like to make to my students. You don't get an answer if you plug in 0 because you're dividing by 0. You don't get an answer if you plug in negative 6. But if you plug in negative 7, it's going to be a horrible answer, but it's still, you get an answer out of it, even though it's not going to be a very nice answer, right? So any other number can be plugged into that function. So unfortunately, this is not an acceptable, it's acceptable really, but this is not the format of the domain that MathXL or MyMathLab is asking for here. It wants the answer in interval notation, right? So I think the easiest way to get the domain in interval notation is to graph it on a real number line. So I'm not graphing this function, I'm just mapping out the domain on a real number line, right? So here's 0, here's positive 6, here's negative 6. I want to skip over all those numbers. And we've done this in the past. I can't remember what problem it was on, but where we want to skip over one number in particular. And the best way to illustrate that on a graph is to put an open circle above that number. So open circle above all three of these, right? Because I want to skip over all three, and then shade everything else in, right? So I'm shading in all the numbers to the left of negative 6, between negative 6 and 0, between 0 and 6, and then all the numbers to the right of 6, right? Shade everything else in, and just have open circles above the numbers that you're wanting to skip over. And then you want to describe these shaded regions using interval notation, right? So this region here goes from negative infinity to negative 6. This region here goes from negative 6 to 0. This region here goes from 0 to positive 6. And this region here goes from 6 to infinity. And then we put unions to join all these intervals together, and this is the domain. And it gets a little ridiculous, right? So if you want to skip over 3 individual numbers, that's going to chop your domain up into 4 separate intervals. And while it's a little bit silly to have to write out those 4 separate intervals, and I would say if you were skipping any more numbers in this, it would just really be silly to use interval notation. Because if you're skipping over like 4 numbers, you're chopping your domain up into 5 different intervals. That's getting a little bit ridiculous, right? Having to write that out. 3 is really kind of the limit of acceptability to me. And I think that's probably the worst case scenario that you'll have on the homework. But what is kind of important about this is that the same thing will happen to the graph of this function. For every number that you have to skip over in the domain, the graph also has a break. So this if we were going to graph this, the graph would exist in 4 different parts, right? It would get chopped up into 4 different parts as well, just like the domain gets chopped up into 4. So if you have to skip over 3 numbers, the graph ends up in 4 different segments, which we're going to see here in just a second. All right, so let's move on to the next problem. I spent 13 minutes on that, which probably only should have took 5 minutes, so that's why my videos end up going way too long. I apologize for that. Let's get to the meat of this section, right? To graph a rational function, we are going to have to find what are called vertical and horizontal or oblique asymptotes, which I haven't defined yet, and I hope maybe I skipped this as well, and that's a mistake on my part. I did, didn't I? Oh, no. Yeah, no, I kind of did. All right, so I guess I'll have to define it here. I don't know if I skipped it intentionally or with the idea that I would just define it as I'm going through the steps here. An asymptote is an invisible line that a graph approaches, meaning it gets closer and closer to that invisible line, but without crossing or touching. that invisible line. And you kind of have to put an asterisk on the end of that because there are occasionally exceptions to that, which makes it really like it's kind of a bad thing to say, well, this is the rule. For an asymptote, the graph never crosses or touches, but sometimes it does. And so you never know, is this one of the sometimes? If so, you have to kind of do a little bit more work to kind of manage that. But then sometimes it's hard to tell if that's going to happen or not. And so, yeah, it's kind of unfortunate that you have to kind of live with that fear that maybe this is one of the asymptotes that the graph does cross once, before approaching without crossing or touching. Even if that ends up being the case, that there is an exception, ultimately, eventually, somewhere in the graph will approach that invisible line without crossing or touching. So even if there is an exception where it might cross it one time, after it does that, then it will approach without crossing or touching. It eventually gets treated as an asymptote at some point, right? So that'll be the first thing that we'll want to find. There are two types, basically. Now, the textbook actually divides it into three types, but I like to organize it a little bit differently. And the two types are essentially vertical, that's one type of asymptote, and then horizontal or oblique is the other type. I like to lump those two together, and you'll see why as we kind of get into the details. So just to kind of give you an idea of what I mean by asymptotes, here's an example of a graph with a couple of asymptotes, and these lines have been made visible to us. But normally when you're graphing this, like if you do this in a graphing calculator like this, you don't usually see these lines. They're invisible. They're not actually part of the graph, but it's nice to be aware of their existence. And so we sometimes will draw them in as dashed lines so we can see those invisible lines because they're kind of like boundaries. They're like barriers that contain the graph. And the graph is going to approach those lines without crossing or touching. So you can see as this graph heads to the right, the purple graph approaches the blue dotted line, right? It gets really close to it. And the pixels do actually end up touching each other. But mathematically, they never touch. Like that purple line never actually touches the blue line. It just gets so close that when you try to draw it out from this vantage point, they kind of start to blend together. But it just keeps getting closer and closer and closer without ever actually reaching it. Again, it's a weird thing with infinities. I say again, I'm thinking of my statistics class where we talk about, infinities in that class as well. But a weird thing with infinity is that mathematically this can happen, that you can, it's Zeno's paradox if you're familiar with that. So, if you want to travel a certain distance, in order to do that, you have to first cover half of that distance, right? And so you get to that point. And now to finish that journey, you have to cover half of the distance that remains. And then to finish the rest of that journey, you have to cover half of that distance and then half of that. And if you're always having to at least get halfway to your destination, you never actually reach your destination. You always just get half as close as you were before. So you get an infinity of halves, right? Now, of course, we know in reality, so mathematically that can happen. You can keep getting closer and closer by half infinitely and never actually reach that destination, right? Mathematically, that can happen in theory, in math, in the world of math. But in reality, of course, that doesn't happen, right? You get half as close, and then eventually you're just so close that you're just there, right? And so in reality, we don't really get to experience that in kind of infinity, but in these graphs we do, right? So this graph keeps getting closer by half every so often, right? But it's always having to cover half of that distance that remains, half of that distance that remains, half of that distance, and it never actually reaches the destination because there's room to keep going half, keep getting closer by half infinitely without ever actually reaching it. In reality, there's not enough room, right? We end up, running out of space. But on the graph, we never run out of space. There's always, between the graph and that invisible line, there's always enough space to get half as close again, and then half as close again, and half as close again without ever actually reaching it. So anyways, going off on a little bit of a philosophical tangent there. Notice the graph treats this invisible line the same going in this direction as well. So, but from underneath, right? So this time the graph comes from underneath and approaches that invisible blue line, getting closer and closer and closer, but it never actually reaches it, despite what this picture kind of looks like. It's just they're so close to each other that when you try to draw it with any kind of width, the pixels will bleed together. But in reality, those points never converge. They never touch each other, and the graph never crosses through to the other side, right? This would be a horizontal asymptote. So that would be that type. And then we have this vertical asymptote where the graph is doing the same thing, heading up and heading down, right? So as the graph, in this case, heads to the left, it goes up against this vertical asymptote, and it, again, approaches without ever crossing or touching. So this is a vertical asymptote. And these occur for different reasons in the graph. So if asymptotes exist in your graph, they are obviously really important to figuring out what the graph should look like, because I kind of think of the asymptotes as sort of the scaffolding that the graph hangs on, right? So the shape, the characteristics of the graph are very strongly determined by where the asymptotes are located. So once you kind of know where the asymptotes are, you plot a couple of points. From there, you know exactly what the graph is going to do. You know the behavior. It's going to approach the asymptotes without crossing or touching, right? So they're really important to be aware of. We need to know where these are located. So that's why that's the first step. Find the asymptotes, right? Then find x and y intercepts if they exist. So not all of these graphs will have an x-intercept. Not all of them will have a y-intercept. And sometimes you won't have either. So you might try to find these intercepts and they just might not exist. And so you can, if they don't exist, then you just say there are none and you just don't have any points from step 2. Whatever points you do end up getting from step 2, you usually will need a couple of more to figure out exactly what the graph is doing. And so step 3 is plot a few more points. Now take advantage of your intercepts. Those should give you some idea of what the graph looks like. But the important thing is you need at least one point in between and outside of all of the vertical asymptotes. Now in the example we just looked at, there's only one vertical asymptote, but you can have more than one. And again, if you have more than one, it chops the graph into more separate pieces. We have to locate where all the pieces of the graph are. Where is the piece of the graph to the left of the vertical asymptotes? Where is the piece of the graph that's to the right? Where is the piece of the graph that's in between these two? To find it, we need points. And really, most of the time, unless there's one of those exceptions where it's crossing the asymptote, 1 point usually is enough. You find 1 point, and then you know from there the graph will approach the asymptotes without crossing or touching. All right, so it doesn't take much. With the asymptotes, you don't really need to find a whole lot of points to have an idea of what the graph looks like. Once you have some points plotted between all of the vertical asymptotes and outside of all the vertical asymptotes, then you want to draw the graph as smooth curves. So again, there's no jagged angles in these graphs that pass through the plotted points and approach the asymptotes without crossing or touching. I put with there. Oh my gosh. I did a really bad job with these notes. All right. Without crossing or touching. All right. So that's the game plan. All right. Let's go back to this example. So I just use this as a visual so you can see what asymptotes look like in a graph. But this is actually a homework question, and it asks us to determine the domain and the equations of the asymptotes. Now the vertical asymptote, you might say, how am I supposed to figure out the domain from this graph? Well, again, the domain is how far to the left, how far to the right. But also, if there's any values of x missing in between, we have to take that into account with the domain as well. And there is a value of x missing. That's why the vertical asymptote is here, right? The graph is avoiding this vertical line. This vertical line, if you'll look, it passes through 1 on the x-axis, right? So on this vertical line, every x-coordinate is 1. And the graph doesn't like it. It doesn't like x equals 1, right? It's being forced. So I kind of think of it like the graph is being pushed up against that vertical line, but it doesn't want to get near it, right? It's trying to like keep its distance as best it can while at the same time having to go in that direction, right? And so however you want to think of it, the graph does not like x equals 1. It's avoiding that vertical line, and this vertical line represents the value x equals 1 because every point on that vertical line, the x-coordinate is 1. And so that's the number that x is not allowed to equal. So for the domain, we can see in the graph that x is not equal to 1. So the domain goes forever to the left, forever to the right, but it skips over the number 1. This graph does not have a single point where the x-coordinate is equal to 1. The graph avoids that. Right? So the domain would be negative infinity to 1, and then 1 to infinity. All right, so that'd be the domain. Oops, okay, I did a bad job of that. Okay, now, the equations of the asymptotes, this would be the equation of the vertical asymptote. So the vertical asymptote, the equation is x equals 1. So that would be the equation of that. For the horizontal asymptote, it looks like it's passing through 4 on the y-axis. And so for a horizontal line, it's y equals a number. In this case, that number is 4. And so that would be the equation of the horizontal asymptote in this graph. All right, let's take a look at an example of graphing a rational function. Okay, I saw this too, but so we're not quite ready to graph one of these rational functions because we have to talk about how to actually find the asymptotes in order to do that. So to find the vertical asymptotes of a rational function, you set the denominator equal to 0 and you solve for x. And whatever solutions you find, those will be your vertical asymptotes. This should sound familiar because this is what we were just doing to find the domain of these rational functions. So the restrictions to the domain are what cause the vertical asymptotes to exist. If x is not allowed to equal 5, then there will be a vertical asymptote in the graph at x equals 5. So finding the domain and finding the vertical asymptotes, it's the same thing. It's the same process. All right, so that's how we'll find the vertical asymptotes. To find the other type, so I used to call these type 1 and type 2. I don't know if that worked very well for students. Again, the textbook doesn't refer to them that way. But again, I like to keep things as simple as possible. And conceptually, it's simpler to think of the horizontal and oblique asymptotes as one type, because there's only ever one of these, and it will either be horizontal, almost said the other word first, or oblique, right? It's going to be one or the other. You'll never have both horizontal and oblique in the same graph at the same time. And the way you find that horizontal or oblique asymptote is to divide the denominator into the numerator and take the quotient as your asymptote, right? So y equals whatever the quotient is will be this type of asymptote in your graph. And it'll either be horizontal or it will be oblique. And it's the only one of this type, right? So that's keeping it simple. That's the simple concept here, is just take the denominator, divide it into the numerator. That's how you can always find this particular type of asymptote. However, dividing isn't always easy, and there are shortcuts. And so I'll explain the shortcuts, but if you forget these, this is why I like to talk about the concept, because it really is a pretty simple concept. You just divide, even if that's not always easy to do. The concept is easy enough. But there are shortcuts. But if you forget them, you can always fall back on the basic idea. Take the denominator, divide it into the numerator. Whatever the answer is for the quotient, that will be the asymptote. All right. Now the shortcut here is if the degree, remember the degree is the highest power. If the highest power on top in the numerator is smaller than the degree on the bottom. So if the highest power of x on top is smaller than the highest power of x in the denominator, then the asymptote will automatically be y equals 0. That's because if the degree in the denominator is bigger, it's too big of a polynomial to divide into the polynomial in the numerator. And so it's too big. It's like taking 5 divided into 2, right? 5 is too big to divide into 2, so your quotient there is just 0. So it's the same thing with polynomials. If the degree on the bottom is bigger than the degree on top, it's too big to divide into that polynomial, so the quotient's just 0. And so y equals 0 will be the asymptote, right? So that's one shortcut. The other shortcut is if the degrees are the same. So if the degree in the numerator is the same as the degree in the denominator, then the asymptote you will get of this type is y equals the ratio of the leading coefficients of those two polynomials. So you'll take the leading coefficient on top divided by the leading coefficient on the bottom. Y equals that ratio. That'll be the asymptote. So that's another shortcut you could take. There is no shortcut if the degree on top is bigger than the degree on the bottom. In that case, you just have to divide. So what kind of bugs me about the way this topic is approached is that there is a scenario where you have to know the basic idea anyways, right? So yeah, there's nice shortcuts here, but those don't always work in every case, right? And so you have to know the basic idea, which is that ultimately you get the asymptote by taking the denominator and dividing it into the numerator. You have to know that for the case where the degree on top is bigger than the degree on the bottom. So you might as well know that that works in every case, right? That will always find the asymptote for you, right? Okay, so to find the x-intercepts, you just set the numerator equal to 0. So this is a little bit of a shortcut for x-intercepts. The denominator plays no role in finding the x-intercepts of a rational function. Because for a rational function, if you're trying to find the x-intercepts, you're setting y equal to 0. So you're having a fraction that is equal to 0. The only way a fraction can equal 0 is if the numerator is equal to 0. The denominator has no say in it whatsoever, right? The denominator could be any number. As long as you get 0 on top, 0 divided by any number is 0. And that's the only way a fraction can equal 0. So to find the x-intercepts, you can ignore the denominator, just focus on the numerator, set the numerator equal to 0. And I kind of like that because it kind of, again, we're extracting all this information. I can't remember how I normally say it. There's some phrase I like to use, but we are, we're using this function to try to extract as much information out of it as possible. So you get one piece of information by setting the denominator equal to 0. That's the vertical asymptotes. And you get another piece of information by setting the numerator equal to 0. That's the x-intercept. Right? So every part of it's getting used to extract as much information as possible. All right. Now, finally, we're ready for an example. And this, again, this has been the theme of all of chapter 3. Do this and this and this and this and this and this and then graph, right? That's a pretty common type of problem in chapter 3. And that's exactly what we're encountering here. So find all the asymptotes, both vertical and horizontal or oblique, the x-intercepts and the y-intercepts for the graph. Now they put y-intercepts plural, but for it to be a function, there can't be more than one of those. So the y-intercept, if it exists, right, there may not be any x-intercepts, there may not be any y-intercepts, right? We have to just kind of wait and see. For the graph of this rational function and then sketch the graph of the function. All right, so we'll stop. We'll go through the process, which is pretty much outlined here. Step 1, find the asymptotes. Remember, there's 2 types. So we need to find the vertical asymptotes. All right, and to do that, we'll take the denominator and set it equal to 0. So we're going to take x squared minus 36, set it equal to 0, just like you're finding the domain. That's exactly how you find the vertical asymptotes. And then it's a quadratic equation, but I was going to say it's a polynomial equation. Thankfully, we can factor it. Or you could just solve it for x. You could add the 36 over, take the square root of both sides. I get a little bit nervous about that because some students will forget the plus or minus. If you factor it, you don't forget it, right? You get both answers if you factor it correctly, right? So it factors as x plus 6, x minus 6. You set each factor equal to 0. I'll just kind of skip the details because we actually did this exact problem earlier in the video. You get negative 6 and you get positive 6. Again, that's what x is not allowed to equal, but that becomes my vertical asymptotes, right? So x equals negative 6 is a vertical line that the graph is not allowed to touch or cross. X equals positive 6 is a vertical line that the graph is not allowed to cross or touch. And those vertical lines, I kind of think of them as like knives, like they chop the graph into separate pieces because it completely cuts off the parts of the graphs from each other, right? So if you draw the vertical asymptotes, right, so let's just go ahead and kind of take this information and do something with it right away. Right, I don't know if I need that much space or not, but we have positive 6 over here, and we draw an invisible line through that, right? This is going to be one of our vertical asymptotes, and we have negative 6 over here. I'm sorry, that kind of looks like a 0. Okay. And so this will be x equals negative 6, which is our other vertical asymptote, which again chops the graph into separate pieces. So how many separate pieces do we have? Well, we'll have one piece of the graph over here to the left of the vertical asymptotes. So there should be some graph over here in this region, which it's our job to find. There will be some graph over here on the right-hand side to the right of the vertical asymptotes. and then there will be a separate piece of the graph in between the vertical asymptotes. And so our job will be to track down where all those pieces are located and what those pieces look like, right? So we have to actually, so it's kind of like we're graphing 3 different graphs at once, right? We have to graph the part of the graph that's over here. We have to draw the part of the graph that's in the middle. We have to draw the part of the graph that's on the right-hand side. And to do that, we need points, but also the horizontal or oblique asymptote would be helpful, right? So let's go ahead and find that. So let's do the horizontal or oblique. So remember, you can kind of lump these together as the other type of asymptote. And again, if you don't remember the shortcut, you can always just fall back to the basic concept, which is to find this other type of asymptote, you take the denominator, which is x squared minus 36, and you divide it into the numerator, which is 1. Now it's important that you set that division up in the right order. So a lot of times students will take the smaller one, divide it into the bigger one, but that's not how you find necessarily how you find this second type of asymptote. It's the denominator, whatever that is, divided into the numerator, whatever that is, right? And so we end up getting this kind of weird division, x squared minus 36, and we're trying to divide that into 1. Well, that's not going to divide into 1, right? There's too many powers of x here to divide into just the number 1. And so the quotient there is just going to be 0. It just doesn't divide. And so y equals that quotient is going to be the asymptote. So again, and which is what the shortcut would have told us, right? The degree of the numerator is 0. There's no variables here, so there's no powers of x. The degree of the denominator is 2. Let's try that again. All right. The degree of the denominator is 2. So the degree on top is smaller than the degree on the bottom, right? And so if that's the case, the asymptote's automatically y equals 0. So that's how the shortcut would be used to figure that out. Now y equals 0 is this horizontal line along the x-axis, right? This is where y is equal to 0. That will be the horizontal asymptote. Now, as far as exceptions go, so I mentioned earlier that sometimes there's an exception. The graph can cross the asymptote once. That never happens for vertical asymptotes. There are no exceptions to that type of asymptote. The graph under no circumstances can cross or touch these vertical lines. But it's the horizontal or oblique one that sometimes has an exception. It's sort of usually it's a good boundary, but sometimes it can be crossed once, right? Okay, so that's step 1. Find all the asymptotes. The vertical ones, again, there could be more than one. In this case, there was 2. And the horizontal or oblique one, there can only be one of those. Now, this one's horizontal, and I need to kind of point this out because on Math Excel or My Math Lab, whichever software we're currently using, it'll ask you for each. It'll say sometimes, not every time, but sometimes it'll say, what's the horizontal asymptote? Well, in this case, we have one, right? It's y equals 0. That's a horizontal line. It's a horizontal asymptote. And then if it asks after that, what's the oblique asymptote? You'll say there is none. There is no oblique asymptote this time, right? So for oblique, there are no oblique asymptotes. Now, you might be saying, what? I've said oblique so many times and I haven't even said what that is. So I'm sorry about that. It just means a diagonal asymptote. It'll be diagonal like this. It's still a straight line, but we have horizontal, we have vertical. Oblique is just a fancy word for like diagonal. It goes at an angle, right? And that only occurs if there's a variable in this asymptote. So if we had like y equals x or something like that, that would be an oblique asymptote. If we had y equals x minus 2, that's oblique, right? So if you have x somewhere in here, if it's just a number, that's always going to be horizontal. Okay, so step 2, find the intercepts, both x and y intercept. So let's do the y intercept first. We're going to plug in 0 for x. And again, I didn't really go through the steps again, but we've seen it a couple of times in this chapter, and it's a review of what we talked about in chapter 1. So we've seen it multiple times in the course, and the steps are no different here. How do you find a y-intercept? You set x equal to 0, then you solve for y. Right? And again, f of 0 is your y variable. Right? So you're going to plug in 0, and it's kind of a weird outcome, right? But 0 squared is 0. 0 minus 36 is going to be negative 36. The 1 on top stays 1, right? So step 2 for finding the y-intercept is, solving for y, and this is what we get. And so we plugged in x equals 0, that's step 1, and we got y equals negative 1 over 36. So my y-intercept is 0, comma, negative 1 over 36. All right, so that's the y-intercept. Let's see if I have enough room here for all this. I'm trying to stay as organized as I can. I'm sorry, I'm not the most organized person. For the x-intercept, or intercepts. Now, x-intercepts, there can be more than one. We want to first plug in 0 for y. So remember, f of x is the y variable. And so when we do that here, we're going to get 0 equals 1 over x squared minus 36. Let's try that 3 again. Minus 36. All right, and so we want to solve this equation for x. And you do see there's an x squared in the denominator, but it does nothing. It has no control over making this fraction equal 0. Right? If you multiply the common denominator to both sides, x squared minus 36, x squared minus 36, it just disappears, right? Because 0 times x squared minus 36 is still 0. And this will cancel out, and we'll just get 0 equals 1, which doesn't have a solution. So as I mentioned earlier, the shortcut for the x-intercept is you can just set the numerator equal to 0. You can just drop the denominator, right? So when I set y equal to 0, the only way a fraction will equal 0 is for the numerator to equal 0. Right, so I'm trying to enumerate these steps. So step 1, set y equal to 0. Step 2, solve for x. Well, you end up getting no solution. Sorry about that. Let's try that again. What am I trying to say here? I want to say none, no solution. There's no x-intercepts this time. And so that's what you would type in, not type in, but you would select that option on Math Excel or My Math Lab. So there'll be two options there. One is the x-intercepts are blank. The other one is there are no x-intercepts. That's the one you want to pick this time. There are no x-intercepts, which kind of makes sense because the asymptote is located on the x-axis. So that makes it less likely that the graph will cross the x-axis because this is kind of acting like an invisible boundary that the graph wants to approach without crossing or touching. Again, sometimes there's exceptions, but this actually tells me there's no exception this time. The graph will not touch or cross the x-axis. All right. Okay, so that's step 2, finding the intercepts. But we do have this one here at 0, negative 1 over 36. So if we plot that point, it's negative. The important thing there is that it's negative, but it's a very tiny number. So it's just going to be just below the origin right there, right? So even closer than that, but I can't mark it any closer without it looking like it's right at the origin. It's just going to be just a hair below it. All right. And that kind of, this will help me figure out what the graph looks like here between the vertical asymptotes. So, which brings me to step 3, right? I'm trying to find the part of the graph that's on the left-hand side, on the right-hand side, and in the middle. And to do that, I need points. I tried finding points from the intercepts, but all I got out of that was just this one point here. And even this one, well, I guess it's pretty clear, right? Because we said it doesn't cross the x-axis. So this tells me that the graph has to stay below the x-axis. It cannot cross above it because then there would be x-intercepts, and we know there aren't any. So even this point actually, even that, it's just one point, but I know what the graph looks like because of that one point and because of the asymptotes. I have an idea of what the graph looks like. What's going to happen is from this point, the graph will approach the asymptotes in the area without crossing or touching. So as the graph heads to the left, it's going to approach this vertical asymptote heading down without crossing or touching. And as the graph heads to the right, it's going to do the same thing. Okay, so it's going to do something like that. Now, is this perfect? My hunch actually is that the graph is pretty flat until it hits in this corner right here, and then it heads down real dramatically. I bet that's what it really looks like, but I'm just gonna, draw like this, and this is good enough. This is a pretty good idea of what the graph looks like. But if you really wanted to know, like how close does it stay to the x-axis before it heads down, you might plug in a number for like x equals -5. Not plug in a number, but pick x equals -5, plug it into the equation to find a point here to see, does it dip down pretty low by the time it reaches here, or is it still pretty high up? My guess is it's still pretty high up here, but I might be wrong about that. All right. And same thing over here, right? If you choose like positive 5 for x, plug that into the equation, you probably find the point still pretty high up here. So I think probably in actuality, the graph does something more like this, like really high up, and just really dramatically heads down as it hits that vertical asymptote. But either way, it's still a pretty good drawing either way, right? We have a pretty good idea of what the graph is doing right here. And so I'm sorry, I kind of missed the point there a little bit when I drew these two lines. So let me just make the point bigger. This is a little trick I've learned with when you're graphing by hand. If your drawing kind of misses one of your points, just make the point a little bit wider so that it reaches back to the graph. That's kind of a cheap trick, but okay. Now you might say, okay, I've graphed it, but I haven't. I've only graphed a third of this graph, right? I still don't have the left-hand side. I still don't have the right-hand side. The only way to find that is to plot points. So actually, let's just head up here to do that, right? So this is step 3. Plot points in any regions that you don't have any points so that you can figure out what the graph is doing in those regions, right? So I need to figure out what the graph is doing over here on the left-hand side. So I will choose a value of x in this region. It looks like the best choice there is going to be -7, right? That's as small as I can make it before I hit the vertical asymptote. So I'm going to choose x equals -7, plug that into the function to find y, and that's going to give me a point. And that's all I really need here. One point is going to be enough for me to know what the graph looks like. Because once I have that point, the graph will emanate from that point, approaching the nearby asymptotes without crossing or touching. Okay. So we're going to get 1 over, this will be 49 minus 36, which is going to be 1 over 13. Positive 1 over 13. So we get the point -7, comma 1 over 13. Again, it's kind of a crazy number, but what's really significant about that number is it's positive, right? Which means that the graph will be above the x-axis. And this point's just going to be a hair above the x-axis, but I know it doesn't cross or touch the x-axis, so that means the graph over here on the left-hand side just stays completely above the x-axis and just approaches the nearby asymptotes without crossing or touching. So here, heading to the right, it's going to hit the vertical asymptote right away, and it'll have to approach that without crossing or touching. And as it heads to the left, it's going to ride along the x-axis, getting closer and closer without crossing or touching, right? So it's going to do something like that. Right. On the right-hand side, we could choose x equals +7, right? That'd be a really good choice here. Plug that into the function, so we'll get f of 7 equals 1 over 7 squared minus 36. That's going to be 1 over 49 minus 36, which is, again, going to be 1 over 13. And you can see there's actually some symmetry here. I think this function is actually an even function, so it's symmetric to the y-axis. So we end up getting 7 comma 1 over 13. Again, that's positive. That places the point just above the axis right here. That's a little bit too high up, I feel like. A little bit closer. And then from there, it'll approach the asymptotes without crossing or touching. So heading to the left, it's going to approach that vertical asymptote without crossing or touching. Heading to the right, it's going to approach the horizontal asymptote without crossing or touching. So like that. Kind of, okay, that's bugging me a little too much. It's a little too close there. Let's try that one more time. Okay, this is better. Okay, I can live with that. All right, and so this is what the graph looks like, right? So it has this kind of shape to it. Now I'm still kind of bugged by that. I don't know. This doesn't look right to me. I'm going to try to fix it one more time. All right. Oh, geez. I'm just making it worse and worse every time I draw it. Let's just do... Oh, gosh. Okay. I'm sorry. I'm wasting time on the video. Okay. Why can't I do this? What's wrong with this thing? Okay. Let's try it one more time, please. Oh, geez. Okay, I'm just going to leave it. You get the idea. I'm trying to make it look symmetric to this, too, and it's just, I botched it. But you get the idea of what it should look like, hopefully. So, all right, let's take a look at another example. Okay, same set of directions here. Find all the asymptotes, the x-intercepts, the y-intercept, if it exists, if they exist, for the graph of this rational function, and then sketch the graph of the function. All right, so let's start with the asymptotes again. This one we actually can just tell by looking at the vertical asymptote. Man, my handwriting's getting horrible. The vertical asymptote, we take the denominator, set it equal to 0, but we can already tell what number is going to make this denominator equal 0. It's going to be 1, right? And so if you can just see that by looking at it, that's perfectly fine, right? X equals 1, that's the vertical asymptote. So again, the vertical asymptote's just like the domain. What numbers would make you divide by 0? Those will be your vertical asymptotes. And if you can just tell by looking, then that's fine, right? That's the vertical asymptote. There's only one this time. So in the last example, we had 2. This time we had just 1. In the first example we did for the domain, there was 3 numbers that x wasn't allowed to equal, so that graph would have had 3 vertical asymptotes. All right, now for the second type of asymptote, horizontal or oblique, again, there's a shortcut this time that we could use because the degree on top is 1 and the degree on the bottom is 1. Right? The highest power of x in both cases is 1, which means they're the same, and there's a shortcut for that. But in case you forget that shortcut, just remember, you can always fall back to the basic concept, which is you take the denominator, which is x minus 1, and you divide it into the numerator, which is 2x plus 1. And the way we do this division, in fact, for this one, you could even use synthetic division because it's of the form that synthetic division is allowed to be used. But if you're doing it by long division, you ask yourself, what do I multiply to x to match the 2x? You multiply by 2. Now there's more to the process. You would take the 2, multiply it to the x, multiply it to the 1, subtract, do all that stuff. But we don't really care about the rest of it. For the asymptote, all we care about is the quotient. The quotient is the asymptote. I don't need to find the remainder for this, for this thing that I'm looking for. I'm trying to, thing is a horrible word choice there, but for this, thing that we're looking for. I can't think of another way to say it. All right. We don't need the remainder. We just need the quotient. And again, the quotient is 2, but to make it the asymptote, you take y equals that quotient. So y equals 2 is the asymptote. It's this other type of asymptote, which again is horizontal because it's a number. It's y equals a number. That makes it a horizontal line. So again, if Math Excel asks, what's the oblique asymptote? In this case, you would again say none. There is not a diagonal one because it's horizontal instead. There's only going to be one of these. It will either be horizontal or oblique. This time it's horizontal, so there's not an oblique one. All right, now we could use this information to go ahead and start sketching our graph. All right, so it's going to look something like this. I'm sorry, my drawings are getting horrible. Let's see, x equals 1. So here's 1 right here. We draw a vertical line through that value of x on the x-axis, right? So this is the vertical line where x is equal to 1. That's my vertical asymptote. The horizontal asymptote is y equals 2. So that's going to be right here. And so that'll be my horizontal asymptote. So I draw a dotted line because it's supposed to be invisible at x equals 1 and at y equals 2. Right. So this is y equals 2. That's the horizontal asymptote. Then, so that's the first step. Second step is to find intercepts if they exist. So let's maybe do that over here this time. Right. So let's do y-intercept first again. So we're going to plug in 0 for x. We get 2 times 1, plus 1 over 0 minus 1. Right. Now the 0 stuff all goes away, and what we end up getting is 1 over negative 1, which is negative 1. Right. So I plugged in 0 for x. I got negative 1 for y. So my y-intercept is 0, negative 1. All right. And so we can plot that point, 0, negative 1. It would be about right here, negative 1. And so we'll plot that point there. And so there we go. We have a point. And again, from here, the graph's going to approach the asymptotes without crossing. So just with that one point, using the asymptotes as a guide, I really have a pretty good sense of what the graph looks like on the left-hand side already. However, you can kind of tell probably what's going to happen is it will also cross the x-axis. And so it'd be helpful to have that point also. And not only helpful, but we're being asked specifically to find any x-intercepts. So we need to go ahead and do that. So I guess maybe I'll do that right here. I don't know. Sorry, I'm not being organized with paperwork. It's just never been a strong suit for me. I think I've gotten a little bit better over the years, and you can see in my work, same thing. I'm a more of a function over form type of person. So as long as I know where everything's located, it's good enough for me. It doesn't have to look nice as long as it's functional, as long as I can get my job done. Same thing with my math, right? I don't have a good organization for like where I put all my work, but as long as I know where it is and I'm getting the information I need and getting the right answer, that's all that matters, right? X-intercept. Right, we're going to set y equal to 0. That's a poor color choice here. Let's do this one. 0 equals, so again, this is y right here. I'm setting that equal to 0. So I get 0 equals 2x plus 1 over x minus 1. Let's go ahead and use our shortcut here, right? Our shortcut is that we can ignore the denominator. It has no say in this fraction equaling 0. The only way the fraction will equal 0 is if we can get the numerator to equal 0. So let's just focus on that. Right, so we need 2x plus 1 to equal 0. Right, so let's solve this. I did not plan this out very well. Subtract 1 from both sides. We get negative 1 equals 2x. Divide by 2 on both sides, and we get x is equal to negative 1/2. Right, so we set y equal to 0. We got x equals negative 1/2. And so we put those together to get our point, which is going to be negative 1/2, comma 0. And that's the x-intercept. I just feel like I have such a hard time drawing zeros on this thing for some reason. It never connects back up. You see how like I'm missing it there? I'm sorry. I don't know why I'm being so picky about it today. All right, that's a little bit better. Okay. So that gives me another point to graph. So let's go over here and graph that point. And it really only serves to enhance our graph on the left-hand side, right? So again, if we think of, let's do this in green again, keep the colors the same. If this is negative 1 here on the x-axis, okay, that's bugging me now too. Okay, maybe I just need to take a break for a while. I just need to get this stuff done though. In fact, I mean, just to kind of let you guys know this, I still have to do the test review for chapter 3 for college algebra, but this is actually the last lecture I need to record. So I'm kind of excited about that. Maybe that's why I'm being a little bit impatient. I just want to get this done, but I don't know why it's bothering me when I'm not writing them perfectly. But it gives me that point there. And again, that kind of might look like a straight line kind of thing, but 2 points always look like a straight line, right? So what we want to do from these points is approach the asymptotes without crossing or touching. So it's going to head down this way as it goes to the right. It's going to hit this vertical asymptote pretty quickly and approach that one without crossing or touching. Now, this is one where we might want to be a little bit careful, like, because it could possibly cross the horizontal asymptote once and then like approach without crossing up here. So you might plot another point a little bit further down, like maybe like -3. And if it stays below that horizontal asymptote, then there's no risk of it crossing over. Because if it's going to cross, it usually does it in a pretty dramatic fashion so that it can go ahead and get to the business of approaching without crossing at some point. Right. I'm pretty sure this one doesn't cross. Let me kind of think that one out real quick here. So if I plug in -3, I'll get -6 plus 1 on top, -3 minus 1 on the bottom. That's going to give me -5 over -4, which is going to be positive like 1.25, which is still below 2. So it's still going to be quite a ways below 2. So it's really gradually approaching this horizontal asymptote, which means it's not going to cross somewhere later down the line. So it's going to do something, oh gosh, okay, let's try that again. It's going to do something like this, oh gosh. Oh, that is so horrible. That is like the worst drawing I've ever done. Let's try to approach it from the other angle. Let's do it like this. Yeah, for some reason, I'm able to go from left to right a lot easier than right to left. I don't know, I'm just not doing a good job of that, usually. Okay, so that connected the points up pretty nicely there. All right, so again, I plotted another point, but I think I felt pretty comfortable that I didn't have to worry about it, but I just wanted to make sure. So I plotted another point just to make sure. So we have the left half of this graph nailed down, right? This is a pretty good drawing of that. What we don't know, because remember, the vertical asymptote splits the graph into 2, right? And we got the left half of it pretty well at this point, but we don't know anything about the right half of this graph. Now, oftentimes, there is sort of a balance to these graphs. So if this one's below the horizontal asymptote on the left-hand side, then on the right-hand side, it's probably going to be above. I'd be really surprised to see it down here, even though I guess that maybe could happen technically. So to be safe, we should plot some points. And this is what step 3 is about, right? So step 3, plot some points in any regions that you don't have the graph already figured out. And so you can figure out the what the rest of the graph looks like, right? So we need to figure out what the graph looks like over here in the region on the right-hand side. So I need to choose a value of x from over here. It looks like 2 would be the best choice. So I'm going to plug in x equals 2 to this function, right? So we'll get f of 2 equals 2 times 2 plus 1 over 2 minus 1. And this is one of the rare cases where this actually works out nice. You get 5 over 1, which is 5, right? So we get the point 2 comma 5, right? X is 2, y is equal to 5. We can plot that point. It's above. The important thing is to know whether is it above the horizontal asymptote or is it below. This is going to be above because the horizontal asymptote is at 2. This point goes all the way up to 5. So this is 2, 3, 4, 5. 5's way up here. So 2 comma 5. It's clearly way above. So from here, it'll approach the asymptotes without crossing or touching. It doesn't have to like get into the corner of where the asymptotes cross necessarily. So I usually just kind of draw like a rounded corner, however far away the point happens to be, just kind of round that corner as you're going from one asymptote to the other. And so this is what I would expect the graph to look like. All right. And so that is the graph for this one. Let's take a look at another example. Okay, so for this example, I'm going to suggest the directions only say find the oblique asymptote. So this will be our first, and it looks like, 'cause I was looking ahead just a second ago, our only example of a problem with an oblique asymptote. So I want to actually explore what that graph looks like having that oblique asymptote instead of a horizontal one. Now on the exam, I don't think I would give you a rational function with an oblique asymptote. They're already fairly difficult even for the simpler asymptotes. So, but on the homework, you'll see some of these, right? And I might give you one where you don't have to graph it. So I should walk that back actually. So I think you do in fact have a problem on the exam where there is an oblique asymptote that you have to find. It's like this problem. They'll just give you the function and say, find the asymptote. You don't have to graph it. I think there is one of those on the test where the answer is an oblique asymptote. But the graphing part of it you won't have to do. Oh, I guess, okay, what am I thinking here? I looked at the first part and I said, oh, find the oblique asymptote, that's all we have to do. But actually it says sketch the graph, so we actually need to graph it anyways according to the directions here. But on the test, you just have to find the asymptote. You won't be asked to graph for the one that has an oblique one. So just to kind of give you a heads up on that. I probably shouldn't even be talking about it. That's what the review video is. How do I want to say that? That's what the exam review video is for, right? The chapter 3 review, which I'm going to do next. Maybe not today, but the next video, next time I record. All right, anyways, if we're going to have to graph it, we should just go through the whole process anyways. So step 1, find all the asymptotes. Let's start with the vertical ones. Again, this one I can just see what number would make the denominator equal 0? 7. And so that will be the vertical asymptote. Again, the process is take the denominator, set it equal to 0, solve for x. But I don't need to go through that because I can just see exactly what I'm going to get. I'm going to get x equals 7 as my vertical asymptote. I'm sorry. Oh, this is... I'm sorry. This is bugging me again. I don't know. I don't think I have OCD. I'm not... If I do, it's a really mild form. But sometimes I can't let things go. Little things like that for some reason. They bug me. Anyways. All right. So that's the vertical asymptote. Again, only one in this case. I'm also kind of bugged by this now. All right. Let's try that again. Underline. Box. Okay. Now. But now I messed up the C again. Okay. Horizontal or oblique. Now, the directions already gave this away, but the label I give this second type of asymptote is horizontal oblique. It could be one or the other, right? Now, we were already kind of told in the directions what to expect. This time, there is no shortcut. So we had a shortcut. If the degree on top is smaller, it's y equals 0. That's the asymptote. If the degree on top is the same as the one on the bottom, then it's a ratio of the leading coefficients, which I forgot to point out in the last example. But in this case, the degree on top is bigger. There's no shortcut for that. The only way to find this asymptote is to divide. Now you could, again, do synthetic division because this denominator is simple enough for that to be done. But that won't always be an option. So I'm choosing to do all of these by long division because just to review how that process works, because there will be a couple of problems where that's what you'll have to do. All right. Now, what we have to do this by long division is to take or to consider what do I have to multiply to this first term, x, to match this first term here, which is x squared. So what do I multiply to x to get x squared? I multiply by x. X times x is x squared. But remember, you have to distribute it. So x times -7 is going to give me -7x. So whatever you put up here has to get multiplied to both of these. Then we distribute a negative sign because we want to subtract. So both of these will switch signs. The highest power cancels out. That should always happen. And then you combine like terms. Well, there's nothing to combine here. So the 7x just copies down. You bring the next term down, but there is no next term to bring down. So it'll just kind of be this blank space again. Right? And then you repeat the process. What do I multiply to x to get 7x? I multiply by +7. Right? Now, there's more to do to finish the division, but I have the quotient now, right? This is the end of the quotient. There's not going to be any more that will go here. And that's all I need for the asymptote. So I don't really care about what the rest of the division looks like. What I really needed was the asymptote, or not the asymptote, the quotient. The quotient is the asymptote. So once you have the quotient, you can just stop, right? It's y equals that quotient. So y equals x plus 7. That is the asymptote of this type, which is oblique. So if there's a variable here, it's a diagonal line. That makes it an oblique asymptote. So if Math Excel or My Math Lab ask you about the horizontal asymptote, this time you're going to say there's none. There is no horizontal asymptote because it's oblique this time. All right, so now we can graph the two asymptotes. All right, so let's see, where do I want to do that? I'm just doing something different every time. I'm hoping maybe one of these will be better than the others. I don't know. So let's, oh, that was a horrible drawing. Okay, there's the y-axis. Here's the x-axis. My x's look bad too. Okay, just, I don't know, I'm being very negative to myself today for some reason. I'm just critical of everything I'm doing here for some reason. So the vertical asymptote is x equals 7, right? So I'm going to need some room to reach out that far. So 1, 2, 3, 4, 5, 6, 7. Let's say there's 7 right there. It's a vertical line through that value of x, and that's the vertical asymptote, which means the graph gets chopped into 2 halves, right? One vertical asymptote chops the graph into 2. And it becomes our job to locate both halves of the graph. So I need to figure out what the graph looks like to the left of this vertical asymptote and to the right. And it may require that I plot points in both regions in order to do that. Right. Now the oblique asymptote is a linear equation. So we are graphing a line. It's y equals mx plus b, right? So what am I doing here? Okay, so think of this as y equals mx plus b. It's a linear equation. The y-intercept is 0, 7. The slope is 1, which we can think of as 1 over 1. So that means I want to start at 7 on the y-axis. 1, 2, 3, 4, 5, 6, 7, which is up here. And again, I'm going to bubble in that point, but remember, this is not my graph. It's the asymptote which determines what my graph looks like, right? So I'm trying to, it's a graph within a graph, right? That's where things get kind of crazy. So I'm trying to graph the asymptote in order to graph this function that I'm trying to graph. And the asymptote is a line. Starts at 0, 7, and we go up 1 to the right 1. And that gives me another point. And I connect those 2 points with a straight line, but it's an invisible straight line, so I do it as a dashed line like this. And I really didn't leave myself enough room up in this direction over here. All right. And then it goes also in this direction as well. All right. So that's what an oblique asymptote will look like on your graph. You'll have this sort of invisible barrier, this invisible line that the graph will want to approach without crossing or touching, but it's at an angle, right? It's not just like straight across. The next step, even though it doesn't say it in the directions, find the intercepts. So let's go ahead and do that. So let's do y-intercept first. Right, we'll plug in 0 for x. So we'll get 0 squared over 0 minus 7. 0 minus 7, which is going to give me 0 over -7, which is okay. You might say, oh, is there a problem plugging in 0 here? There's not. It's okay for x to equal 0. It's not okay for x to equal 7, but it's okay to plug in 0 because it doesn't make you divide by 0. But I know it sounds similar, but you're dividing into 0, right? 0 divided by -7 is going to be 0. And again, that's okay. You get an answer from that, right? So when I plug in x equals 0, I get y equals 0. So that gives me the point 0, 0, right? Which is going to be right here. And again, that gives me a pretty good sense of what the graph looks like on the left-hand side. Using that point and the asymptotes, I know it's going to approach the asymptotes without crossing or touching. Now, what I'm not entirely sure about is like how it goes about doing that. Is it kind of shallow over here and kind of heads into this area and then heads down? Or is this sort of the peak where it kind of from here branches out this way? So we might want to plot another point just to kind of see if how far into this region here we should go before we start approaching the asymptotes. Right. But there's the y-intercept. What about the x-intercept? Let's try that barrier again there. So the x-intercept, x-intercept, we're going to plug in 0 for y. So again, this is the y variable here. We're going to plug in 0 for that. So this is a y equals 0. And we're going to get 0 equals x squared over x minus 7. Again, the shortcut here is we can just ignore the denominator for finding the x-intercept and just focus on the numerator. So we have 0 equals x squared. To solve that, we take the square root of both sides. And yes, you should do plus or minus when you take the square root of both sides, but plus or minus 0 is still just 0. So you just get x equals 0. So when y is equal to 0, x is equal to 0, and we just get the same point we already had. It's 0, 0. So really kind of not very helpful this time. Right? 0, 0. Same point. So that's all I get out of the x and y intercepts. So that's step 2. Step 3 is to plot points, in between and outside of all the vertical asymptotes. And it's a little bit of an overstatement here because we only have the one vertical asymptote. So I just need maybe one more point over here just to kind of figure out what's going on with that point. And then one or two points on the right-hand side. And then with the asymptotes, I should be able to figure that out. And I'm guessing you could see from my what I'm doing with my cursor is I'm thinking the graph is just going to exist somewhere up here, right? If this one's down here below the oblique asymptote, the balance of it would be this one's going to be above it. But let's find out for sure by plotting some points. Let's do that down here, I guess. So again, I'm not sure the best way to organize all this work. So 3. Plot some points. So let's do another point over here in this region, but I'm more curious because from here, I'm pretty sure there's no x-intercepts here. So it can't go above. I guess that kind of answers my question completely, right? Because the graph cannot go above this point, because if it does, it has to come back down. It would have to cross the x-axis somewhere else, but we just determined there are no other x-intercepts. It should not cross the x-axis anywhere else. Same thing over here, right? It can't go up and then approach the asymptote because it would have to cross the x-axis again. So it really can't go above this point. So I really feel like we don't need any more points in this area now that I think about it. From here, it's just going to approach the asymptotes without crossing or touching. So it's going to look something like that. Right? But what I don't have any information about is the right-hand side of this graph. So I'm going to choose like x equals 8. That's probably the easiest choice to make there. And I'm going to plug that into the function. So I'm going to have f of 8 equals 8 squared over 8 minus 7. And again, it's another rare case of a rational function giving us a nice answer. We're going to end up with 64. It's a nice answer, but it's a big number. We'll get 64 over 1, which is going to be 64. All right, so we get the point 8, 64, which is a big number, but maybe kind of necessary, because what we really need to know is this point above or below the diagonal asymptote? And if it was something like 10 or 12 or 15, that'd be kind of hard to tell. But 64 is pretty obvious. It's above, right? I mean, this line is going up one to the right one. So by the time it reaches 7, we're at 14, right? Because, well, let's think about that. So 1 gets us up to 8. 2 is going to get us up to 9. So it's 2, it's, whatever this number is, add that to 7. That's how high up you are. So when we hit 7, this point here is going to be at 7, 14. So 8 is going to be 8, 15, right? That's the asymptote. The asymptote is at 8, 15. So as long as the number is bigger than 15, it's above the vertical asymptote. If it's smaller than 15, it would have been below. But 64 really didn't even make it debatable. In fact, I can't even fit it in my graph. It's very, very high up. And then from here, it's going to approach the asymptotes without crossing or touching. So the graph looks something like this. And this is really kind of a poor approximation of it because that value for 8 is like off the charts. It may not even really get that close to this region here, but I don't have enough room to draw it appropriately. So I know it's going to look something like this, but it's probably further out where it's doing that at. Anyways, again, and what I do on my lecture video is good enough for your test, right? So if this is the answer you have on your test, even though it's not perfect, I'm going to be more than happy with it. It has all the asymptotes in the right place. You plotted points. You have the right idea about what the graph looks like, even if it's not drawn perfectly. And so I'll be more than happy with that as your answer. All right, I have a couple more examples. So this video is getting a little bit lengthy. I have a couple more examples. So let's go ahead and do, now these are kind of repetitive. They're similar to the problems we've already done. And, you know, usually when I teach this face-to-face, I don't usually cover these problems, but I'm going to go ahead and do so in the video, but in the way that I've done in previous videos. So I'm going to pause my recording, work this problem out off screen, and I ask that you also pause the video and try to work this problem out on your own paper, and then resume the video to check your answers. So I'll see you in just a minute. Okay, so there was a little bit of a difference in this problem I forgot about, something that's makes it a little different than what we did in the earlier problem. So I'm sorry I asked you to do this. Maybe I'm not sorry about it, but there was something different about it. So I don't know how well you were able to manage that difference, but it was a difference that manifested itself in a really obvious way. So hopefully you're able to adjust to it okay. All right, so let's go ahead and talk about how this problem unfolds. First, you find the asymptotes. The vertical asymptote, you take the denominator, which is x squared minus 25, set it equal to 0. Solve it by factoring. So I factored it to x plus 5x minus 5, and then set each factor equal to 0. You get x equals negative 5, x equals positive 5. So there are two vertical asymptotes in this problem. For the horizontal asymptote, and so I should say, well, I guess I didn't really comment on both of these, but it is a horizontal asymptote. There is no oblique asymptote this time. You can use the shortcut. The degree on top is smaller than the degree on the bottom, and so the asymptote's automatically y equals 0. If you forgot that shortcut, what you would do is take the denominator, divide it into the numerator, but x squared is too big to divide into x, so that makes the quotient automatically 0, and that's how we get that type of asymptote. It's a horizontal asymptote. There is no oblique asymptote. All right. So that's how you get the asymptotes. For the intercepts, you set x equal to 0, plug in 0 for x, you end up getting 0 over negative 25, which is 0. So you end up getting the y-intercept is 0, 0. For the x-intercept, you set y equal to 0, which is this right here. Then you focus on the numerator. The only way this fraction can equal 0 is for the numerator to equal 0. So set the numerator equal to 0, you get x equals 0, and so you end up finding the x-intercept is also 0, 0. Now, what makes this problem different from the previous ones is that point, that y-intercept, is exactly on the horizontal asymptote, right? The horizontal asymptote is at y equals 0. This point will be on the horizontal asymptote. And so this is the first example that we're seeing of one of those exceptions where the graph actually crosses the asymptote once. And so we'll see what that looks like in just a second. Now, I'm trying to save the graph for last. What I ended up doing for step 3 was I had to find 4 different points. Because that one point is exactly on the asymptote, I don't know what the graph is doing on either side of that point. So I also found points where x is equal to 1 and negative 1, which is around the x and y intercept, 0, 0. So I could see the behavior of the graph, through the asymptote. And then I found these points because those are on the outsides of the vertical asymptotes. So negative 6 is to the left of the vertical asymptotes. Positive 6 is all the way to the right. Because again, with the two vertical asymptotes, there are 3 different parts to your graph. The middle part is the one I'm finding all these points for, but this is the part of the graph on the right-hand side. This is the part of the graph on the left-hand side. And so I found those points by taking the value I chose for x, plugging it into the function, and then solving for y. So when I take 1, plug it into the function, I get this. I get 1 over negative 24. It's negative, which places it just below the horizontal asymptote. But when I plug in -1 for x, I end up getting -1 over -24, because again, -1 squared is +1. 1 minus, I put 24 there because I knew what the answer was about to be. Sorry about that. I don't know if you guys spotted that mistake there, but let's erase that. All right, this is supposed to be 25 right here, all right? So, but this will be 1 minus 25, which gives me -24. The negative signs cancel each other out, and so we get 1 over 24, which is positive. So when you plug in -1 for x, you get +1 over 24, which is just above the horizontal asymptote. So not only does it, like, is there a point on the horizontal asymptote in the middle, but it actually crosses through, because it's positive on one side, it's negative on the other side, it's crossing through the asymptote. For 6, you plug that in. I did that here. Sorry, wrong button. You get 6 over 6 squared minus 24, and you get a fairly decent answer. You get 1/2, right? You get 6 over 12. So 6 squared is 36. 36. Why am I doing 24? Oh my gosh. I made big mistakes here. So I made that a 24, and then I used 24 for the rest of the problem. It's supposed to be 25, remember? Okay. Oh, this is horrible. Sorry. This is going to add a little time to the video. So these answers are just wrong. My graph is still fine because it's going to be pretty close to where the point already was, but my numbers are wrong. And so this should have been 25. I'm really sorry about that. All right, so we get 36 minus 25. I don't know what's wrong with me today. Here we get, again, 36 minus 25. So in both of these cases, this should not be 12. It should be 11, right? So it doesn't reduce as nice as we would like. All right, and same thing here. Should be, and that answer is not correct. So, and of course, these answers aren't going to be correct. So let's erase those as well. All right, so this is going to be -6 over 11. +6 over 11, and that doesn't reduce. So you get 6 over 11 here, and -6 over 11 here. Right. But that's still really close to 1/2. And where you mark the point on your graph, it's not drawn as so accurately, so precisely that we could tell the difference between 1/2 and 6 over 11. Those are very, very close together, and so the point's not really going to budge at all from where we had it before. So that's what we should have had. Sorry, I made that mistake. That's kind of embarrassing. So now we can draw our graph. So here's the final product. Of course, I didn't draw this all at once. I was building this as I was getting information. So when I found the asymptotes, I went ahead and graphed those first. When I found the y and x intercept, I plotted that point. I realized, oh man, that's when I realized, like, oh, I told them to pause the video and work on it on their own, but we didn't have an example of this happening yet. But there you have it. And because that point is smack dab on the asymptote, we need to plot points around it to see, because anything could have happened here. It could have did this. I've seen graphs that do that, where, it's below on both of these. And so you get this kind of parabola where it reaches the asymptote but doesn't cross through, right? So it only touches. But so just finding one point, you can't just assume the other point's going to go in the other direction. So you have to kind of look for points on either side of that point to see how the graph is behaving with that asymptote being there. And notice that really what's happening here is the graph is treating this horizontal line as an asymptote on the left and right hand side, but it's completely ignoring it in the middle. So this horizontal line is not an asymptote to the graph in the middle of the graph. It only acts like an asymptote over here on the left and on the right. So that's what's happening here. But I still need to plot points to figure out what's this graph doing. So it does this kind of thing here, which is kind of interesting. And then we plotted the other 2 points. For 6, we have 6 over 11, which I thought was originally 1/2. But it's positive, which puts it above. Now, I kind of did a bad job drawing my asymptote here, but it's on the x-axis, right? Just above the x-axis. And I don't need to plot any more points to know from there it approaches the asymptotes without crossing or touching. For -6, we get -6 over 11, which puts it below the horizontal asymptote. And then from there, approaches without crossing or touching. And so that's what the graph should look like. All right, let's do one more. Last example, same thing. Go ahead and pause it. I'm going to pause the recording, work out all the details off screen. Why don't you go ahead and try the same thing? Now, this time we shouldn't have any surprises that we haven't already seen in the video. So we've done every possible thing that can happen so far. Anyways, sorry, I'm getting a little bit, near the end of the video. I start to run out of steam, I guess, and so I'm kind of reaching that point now. But let's go ahead and get this last example done. So pause the video, then resume it to check your answers. Okay, so this example went pretty quickly. So the vertical asymptote, you can probably tell by just looking at the equation, what's going to make the denominator equal 0 is a 3. That's what x is not allowed to equal. That will be our vertical asymptote. So there's only one this time at x equals 3. I get that from the denominator. For the horizontal or oblique asymptote, again, we can use that same shortcut that worked on the last example. The degree on top, which is smaller, it's less than the degree on the bottom, which is 1, which means the asymptote's automatically y equals 0. I didn't even bother writing out the division, right? This is too big to divide into just the number 1, which means the quotient's 0. That's a horizontal asymptote. There is no oblique asymptote for this problem. For the y-intercept, we plug in 0 for x, so we get this, which of course the 0 goes away, so we just get 1 over negative 3, which is negative 1/3. So that's the y-intercept, 0 comma negative 1/3. For the x-intercept, you plug in 0 for y. Again, f of x is the y variable. So you get 0 equals this fraction. The only way the fraction can equal 0 is for the numerator to equal 0, but that's impossible because the numerator always equals 1. There's no way it will ever equal 0, so there's no solution there, which means there are no x-intercepts in this particular graph. Right. See if I can save the graph for last. I don't know if I can. Yeah, it's right over there. I don't know if you guys could see it. It was just off the screen there. And then for step 3, based on looking at the asymptote and looking at the point I already have, which is the y-intercept, I really only need one other point to finish out the graph. And that is a point that's on the right-hand side of the vertical asymptote. So remember, the vertical asymptote is at 3, so I picked x equals 4. It's the very smallest number I could pick that's on the right-hand side of the vertical asymptote. So I plug in 4, and you actually get a nice answer again. You get 1. So when you plug in 4 for x, you get 1 for y. And so I use that point to help me figure out the graph on the right-hand side. And so I end up with this graph right here. So here's the vertical asymptote at x equals 3, the horizontal asymptote at y equals 0, the y-intercept, which is located, and this is maybe a little too low. It's negative 1/3. This looks like it's more than halfway, but it should have been less than halfway. But you get the idea. Negative 1/3 is going to be somewhere between 0 and negative 1. And I don't really need any other points here to figure out what the graph is doing. It's going to approach the asymptotes without crossing or touching. But I needed another point on the right-hand side to figure out what the graph is doing over here. So that's why I chose 4. I get this point 4, 1 from here, approaching the asymptotes without crossing or touching. And that's how I got that graph. So that concludes the video on section 3.5. I will see you in the next video, which will be the chapter 3 exam review video. Thank you for watching.